Yes. So today I want to talk a little bit about two-view geometry and try to wrap up this topic so that we can move ahead with image processing. However, I must tell you that if we are going to wrap it up this way, there are a few things that I will not be able to cover. Okay, but it is possible that after we have done some image processing up to say segmentation and feature extraction, we can come back and look at some details of reconstruction when we look at those topics in image processing itself. Okay, so right now what I'm going to do today is going to talk about first the essential matrix. So this is something I talked about towards the end of the previous lecture. So let me define the essential matrix, state its properties. Number two, although I have stated it here, this is something that I'm going to leave to you. Okay, so two examples of the fundamental matrix in some simple situations. One where the transformation between the two cameras is that of a pure translation, and another where the transformation is a pure planar motion. Okay, so there could be rotation, but the motion is still planar. Okay, so these two examples, this I'm going to leave to you. I'm not going to cover now. If somebody asks or required, then we will have, then I will say something about it later. Number three, this is what I want to talk about: retrieving camera matrices from the fundamental matrix and from the essential matrix. So this is an important point. Then computing the fundamental matrix from point correspondences. And finally, a little bit about reconstruction. Okay, so I don't know how much of this we will be able to cover, but I'm just trying to give you some idea of triangulation. Okay, and as I said, later after we do some image processing, we can come back to this idea. Are there any questions from what we did last time? So last time we talked about the fundamental matrix and how it is derived from the geometry of the two-view camera setup. So I hope you have had time to look through it once. Okay. Well, even if you haven't had in the past week, I hope you will in the coming week, because you also have quiz 1 at the end of this coming week, right? And I have posted some problem sets. Those are still on one single view geometry. Today I will post one set on two view geometry, and so do try to solve those problems. Okay, so that will give you some hold on these concepts. And also I will post the answers, not the solutions, but the answers. And the solutions we can discuss in an extra tutorial or something. If the class asks me to do it, I will try to hold an extra tutorial for solving those problems. Okay, so there will be three total problem sets in that folder by the end of today. Okay. All right, so coming back to the topics at hand, I hope everybody has understood the fundamental matrix from the last time. Okay, so now what we want to do is move ahead and talk about the essential matrix. Okay, so just to recap, what we have seen is that if we have two cameras or two camera matrices, P and P prime, and suppose these are calibrated, which means they have been decomposed as the intrinsic parameter times the extrinsic parameters, right? So both are calibrated. And suppose that the first camera is actually placed at the origin of the world coordinates. Okay, so it's in a special position. The reference camera is in this special position. Okay, so under this assumption, the corresponding fundamental matrix of that configuration is given by this formula. Okay, so you can use this formula where E prime is the epipole in the second image. Okay, P prime is this camera matrix P prime, and P plus is the pseudo inverse of the camera matrix P. Okay, so you can use this formula, and then we showed that this formula can further, using these calibrations, you can further simplify to either this form or to this form. Okay, so this is what we did last time. Now we will use this and try to derive the formula for what is called as the essential matrix. So historically, the idea of essential matrix came first. Okay, So as you will see, the essential matrix is the simplest way of thinking about this entire setting. Okay, and the fundamental matrix was a generalization of that idea. But now when we do these things theoretically, usually, I mean, or at least in this book, the fundamental matrix has been defined first, and as a special case of it, the essential matrix is being defined. Okay, so so for the essential matrix, we need to first talk about the normalized camera. So normalized camera means.
Hello, ma'am.
Yes, is there a
Yeah,
question?
can you rotate your screen for better view?
Oh, sorry. Yes, I should do that.
Also, ma'am, I had one doubt that what will be
Yes.
the syllabus of quiz 1?
So this things up to 2 view geometry.
Thank you.
So maybe whatever we complete up till today, to be more precise, because I'm hoping that in the next class we will start covering image processing. Okay. All right. So is this better?
Yes, it's better.
So the normalized camera, what we do is this is our calibrated cameras, right? So we further make another change in this. So what we do is, since we know the calibration, okay, see, if we are purely interested in the position of the camera with respect to the world coordinates, and we are not really interested in this intrinsic parameter, then a way to look at this is, you look at the matrix K inverse P. Okay, so that is going to give you only this I0. Or in this case, if you take K prime inverse P prime, then you will be left with only R and T. So that in that sense, you will talk purely about the position of the camera in the world coordinates. Okay, so you are sort of ignoring these intrinsic parameters. Then that's called a normalized camera, essentially. So the definition goes this way: you consider a camera matrix decomposed in this way, and suppose X is a point in the image projection under P. Okay, then the matrix K inverse P, okay, K inverse P means simply this RT is called the normalized camera corresponding to P. Okay, and this point, so we are looking at the point X equals PX. So instead, now if you look at K inverse X, okay, so X hat equal to K inverse X, which means this RT applied to X, that point will be the point which is said to have normalized coordinates. Okay, so if the language we will use is, okay, look at X in the normalized coordinates, which means we will be looking at the corresponding X hat. Okay, so that is what normalized camera and normalized coordinates mean. Okay, and in particular, if we are looking at this special camera, which is centered at the world origin and has its axis aligned with the world axis. So that camera, if you normalize, then the resulting camera is called the canonical camera. Okay, so then in that case, the camera matrix is simply this much, right? Even the K is gone and only this much. This is called as the canonical camera. Okay, it's just names for references. Okay. All right, so the fundamental matrix of, now instead of looking at any camera pair, so fundamental matrix was defined for any camera pair. Now you look at the particular camera pair P equal to I0, which means the canonical matrix, and P prime equal to RT, which is a normalized camera. Okay, so you have a normalized camera pair here, with this being the canonical one, the reference camera being the canonical one. So if the fundamental matrix of this kind of pair is called the essential matrix. Okay, and just like so we showed that for fundamental matrix, the definition of a fundamental matrix is equivalent to saying that X prime transpose Fx is 0 for every image pair XX prime. Similarly, for essential matrix, we can make this with normalized coordinates, right? X hat prime E, X hat prime transpose. Okay, it should be transpose. So X hat prime transpose Ex hat equals 0 for all corresponding image points XX prime. Okay, so just like we have those set of equations for the fundamental coordinates, similarly we will have these set of equations for the essential matrix. Okay, is this clear? Yeah, this is so the essential matrix can also be defined by this, the matrix E which satisfies this equation, okay, for every image point, every pair of image points. So let's just try to simplify this a bit. Let's notice that if you substitute x hat equal to k inverse x and x hat prime equal to k prime inverse x, which is what they actually are, okay, then so I've just this substitution simplifies this earlier equation, this equation to this equation. Okay, so in place of x hat prime, I have put x prime k prime inverse transpose, okay, E, and then this is k prime k inverse x. Okay, then we just simplify this. But if you look at this inner term, okay, if so, this is one matrix, and then again here this should be transpose. So if you consider this inner term as one matrix, then we are saying that x prime transpose times this matrix times x is 0 for every pair. That implies that this inner matrix must be the fundamental matrix, right? And so we get this relation between the essential matrix and the fundamental matrix for a given camera pair. Okay, so if you know the camera pair, then the essential and fundamental matrices are related by this relation. Okay. Further now, so recall this, we have this formula. I also stated it in the beginning here, that the fundamental matrix is E prime cross K prime R K inverse. Okay, so where the notations are as usual, and E prime is the epipole in the second image, which means E prime is K prime T. Okay, so this we had derived in the previous lecture. Okay, so now if you are looking at the case of normalized cameras where P is I0 and P prime is RT. So here there is no K. So K is identity, K prime is identity. Okay. So if we want to, so this formula in this case reduces to, in place of F, we will have the essential matrix. In place of E prime, okay. So E prime is K prime T, but K prime is identity. So we will have just T. Okay. And in place of all this, we will have only R. Okay, so this formula for the fundamental matrix simplifies to this formula for the essential matrix. Okay, and this is very important. We will see. Going further, last time we had seen a commutation relation for this kind of matrix, right? So if we want to put this matrix on the other side, then we will have to do this change in R. Okay, so this the latter part of this formula follows just from that commutation relation. Okay, okay, so yeah, so the only question here is, why is this R transpose T? Okay, so if you look at the formula here, okay, so it is clear where R is coming from, and you might want to, either you can look at the commutation relation, or you can look at this formula and see that this is E. Okay, so then this is another way of looking at or getting this formula, which is that, well, notice that E is PC prime, right? The projection of the second camera center through P. So this is P, and C prime is the camera center of that calibrated matrix. So we know that C prime is the vector minus R transpose T 1. Okay. So now if you apply P to this matrix, well, P is I0 here. Okay. So applying P to this matrix is going to give you minus R transpose T. Okay, but minus R transpose T, you can even, or you can simply say R transpose T, because you're looking at this in homogeneous coordinates. So that is how you can, in place of E here, we have R transpose T. So that's another justification for why this is true. Okay, so this is a formula that we get for E in terms of the translation and the rotation. Okay, so now moving ahead, so this is something that we are not going to show, but you can look up if you are interested. So it can be shown that a 3x3 matrix is essential if and only if two of its singular values are equal and the third is 0. Okay, there is a I can give you some sort of justification, but the proof you can go through if you are interested. So what I'm saying is that a 3x3 matrix, or any 3x3 matrix whose two of whose singular values are equal and the third one is 0, is an essential matrix of some camera configuration. Okay. So what goes into proving this is the following fact. So one, that E is written in this way. Okay. Then this matrix we have seen is skew symmetric. Remember, for any vector that you put inside here, the cross product with that vector, we have seen that we can express that as a matrix, and that matrix is skew symmetric. So what we have here is a skew symmetric matrix, and here a rotation. So essentially this formula is telling us that the essential matrix can be factorized as a skew symmetric matrix times a rotation matrix. Okay, and the proof of this theorem or this result hinges on the fact that any matrix that can be factorized as some skew symmetric S times a rotation R will have singular values, two equal singular values, and the third 0. Okay, so yeah, that's what I've written here. In particular, this matrix is skew symmetric and gives a factorization of E as E equal to SR. And it can be shown that any 3x3 matrix SR has two equal singular values and third equals 0. Conversely, any matrix that has this property will split as S times R, a skew symmetric matrix times a rotation matrix. Okay. So this can all be shown using SVD essentially. Okay. So the proof is not too difficult, but slightly lengthy. And since we don't really need to go through it, so I'm not going through it. But the point to remember is this, okay, that S times R, a skew symmetric matrix times a rotation matrix. That's how any essential matrix looks like. Okay. So any questions here about the essential matrix? I've covered the three main properties of the essential matrix, okay, and the definition. Do you have any questions about this? Okay, so if there are no questions, then I will so as I said, there are a few things on the agenda today. One was this. This second one I'm going to leave to you. The third one, retrieving camera matrices, and this is important for reconstruction. So we have seen that given camera matrices P and P prime, how to construct F and E. Okay, now we want to look at the inverse or the converse problem, which is if you are given F, okay, then how do you construct or how do you retrieve the camera matrices from F? Okay, so and the same question for E. So it turns out that there is some ambiguity in constructing or retrieving these camera matrices. There is no uniqueness. Okay, so we'll study why there is no uniqueness and then what is the best that can be done. Okay, all right. So first of all, the camera matrix, as we know, will depend on the choice of the world coordinate frame, okay, as well as the camera coordinate frame, right? So both these things are important when we want to determine the camera matrix P. However, the fundamental matrix itself remains unchanged under a projective transformation of the world space, which means that if you apply a projective transformation, so actually here is a nice demonstration of that. So here we have the setting of two view geometry, right? So here we have two cameras, two images, and then a world point X being projected by P and P prime onto these two images. Okay. So now if you sort of what I can do is so this is a configuration, right? This configuration I can use a projective transformation and move this configuration somewhere else in the 3D space, in the 3 space, right? So that moving can be something like this. So this same configuration can be moved somewhere. And it could be, so right now, since I'm doing this on a 2D plane here, I can only show you scaling. Okay. So there is some kind of scaling here. Okay. Or planar rotation. Okay. So a combination of planar rotation and scaling. But you can imagine that these operations can be done. So the rotation can be done, in 3 space. But this is still only similarity transformations. Okay, what I'm doing right now is only a similarity transformation of the given system. Imagine that we could do projective transformations. Okay, so what does projective transformation mean? Okay, so some kind of distortions are also allowed. Okay, your parallel lines will meet at infinity, that kind of thing. Okay, so projection. So instead of having just this similarity transformation, suppose you were allowed a projective transformation. Okay, and that projective transformation is this H. Okay, so the point is that if you have F being the fundamental matrix of the configuration on the left, then under a projective transformation H, you will have the same fundamental matrix. Okay, so the fundamental matrix does not change under a projective transformation simply because we determined F up to up to a scalar. Remember? The determination of F was up to a scalar only. What this means is that your X can change to the point HX. Your P can change to the point, to the map PH. P prime will change to the map P prime H. Okay, everything will, for all elements on the left hand side, you apply H. Okay, and you will get these elements on the right hand side. Okay, but the fundamental matrix will remain the same. So if you're just given the fundamental matrix, you cannot uniquely determine which pair P prime it came from. There will be a family of camera pairs which could generate this F. Okay, so that gives rise to an ambiguity. Okay, and so it has been proved that, however, this is the only ambiguity. Okay, which means the only ambiguity that can happen is that you will have P and P prime determined up to a homography, up to a homography, up to this map H, up to a projective transformation. Okay, there is no other problem. This is the only obstruction for one-oneness. Okay, so these two things we have to keep in mind. One, that F determines the camera pair only up to a projective transformation. And secondly, there is no other problem. So this is the only ambiguity that occurs. Okay, so that is what we are going to sort of look at these statements and reach that conclusion. Okay. So, yeah, that's what I was saying here. A rotation of the world coordinate system will change P and P prime, but it will not change F. Okay, it does not change the fundamental matrix of the configuration. So, so this is what I was saying just now in that with that help of that diagram. That is, if H is a 4x4 matrix representing a projective transformation of 3 space, then the fundamental matrices corresponding to the pairs of camera matrices P prime and PH P prime H are the same. Okay, and the proof is just one line, because, well, notice that PH can be written in this way. You insert this HH inverse. Similarly, for P prime, you can insert HH inverse. Okay, and now if XX prime is a pair of matched points, okay, then they will also be a pair of matched points with respect to PH P prime H. Okay, and they will correspond to, oh yeah, so H inverse X, not HX. So this should have been H inverse X. Okay, so that's what is appearing here. Okay, so then they will correspond to this world point. Okay, so X and X prime will still be a pair of matching points. Okay, so that sort of proves this result. Then moving on. So what the upshot is that the mapping between the set of all camera pairs on the one hand and the set of all fundamental matrices on the other hand, this mapping is not 1-1, because you could have such pairs all mapping to the same fundamental matrix. Okay, so here you can have actually a class of these pairs of matrices mapping to the same fundamental matrix. Okay, and what is the difference between these the pairs that will appear here? The difference is only of a homography, which means the pairs will all be connected to each other through some homography. And this is the only ambiguity, that is, this is the only way in which different camera pairs may correspond to the same fundamental matrix. So that's what this theorem says. Let F be a fundamental matrix and P prime, P tilde prime be two pairs of camera matrices corresponding to F. Okay, then there must be a non-singular 4x4 matrix H such that P tilde and P are related through H, and P tilde prime and P prime are also related through H. Okay. So this sort of settles the question of when you are given F, then what are you determining? What camera pairs are you determining? Okay, so you're determining camera pairs up to homography. Okay, now there is a to still get a stronger handle on P and P prime. Okay, so what we would like to do now is, so we know that if we are given F, we cannot completely determine P and P prime. But then how do we solve the problem? The next thing to do is to see if you are given F and you are given some additional information about one of the matrices, one of the camera matrices, then can you determine this? Okay, so going ahead to that, first we require a characterization of F using P and P prime. Remember, we have a characterization of F using image pairs, image points X and X prime, namely that X prime transpose Fx must be 0 for every image point pair XX prime. Similarly, so just putting that here. So if we know that small x is P capital X for a world point X, and small x prime is P prime capital X, correct? So this is the image point pair, and we already know that X prime transpose Fx is 0 for every such image pair. So just putting this together, okay, now substituting in place of X prime and X, we can substitute these. Okay, so we get capital X transpose P prime transpose Fpx is 0 for all capital X's, right? So what we want to show is that F is a fundamental matrix for P and P prime if and only if P prime transpose Fp is skew symmetric. Okay, so saying that this matrix is skew symmetric is same as saying that this is 0 for every X, right? And saying that this is 0 for every X is same as saying that X, by using the substitution, that X prime transpose Fx is 0 for every X, which is true because F is the fundamental matrix. Okay, so this characterization in terms of image point pairs can be converted to this characterization in terms of the camera matrices. Okay, so F is a fundamental matrix if and only if P prime transpose Fp is a skew symmetric matrix. Now, using this characterization, what we can do is we can obtain a particular solution. So here we have a class of solutions, but we can obtain a particular solution for P and P prime by making a choice. First, you make a choice for P, take it to be this canonical matrix. Okay, and for P prime now, you are given F, remember. For P prime, you choose the matrix SF E prime. Okay, where E prime is an epipole, and how do you find that epipole? It should satisfy E prime transpose F is 0. Okay, because, well, the epipole here, I mean, this is not going to give you the epipole E, right? So we just depend on this formula for defining the epipole. Okay, so you choose canonical matrix P and define P prime to be SF E prime, where S is any skew symmetric matrix. Okay, then it can be shown that F is the fundamental matrix corresponding to this pair. Okay, and using the earlier criterion to show that F is a fundamental matrix corresponding to this pair, all you have to show is that P prime transpose FP is skew symmetric, and that is simply what is being done here. Okay, so this is P prime transpose F and then P, and if you simplify that just as block matrices, then we get this, which is a skew symmetric matrix because S is skew symmetric. Okay, so that shows that we have P and P prime being one solution for a pair of camera matrices given F. Okay, is this clear? Once you have a particular solution, then of course you can generate the entire family of solution by applying any homography. Okay, so in this way, given a fundamental matrix F, we have gotten hold of a pair of camera matrices. Okay, there is of course some ambiguity. Okay, because everything is up to homography, so maybe we can say a few more things about it. One is that, instead of taking any S, so this works for any skew symmetric matrix, but you can make a particularly good choice of S, which is E prime cross. Okay, so we have the epipole, right? We already have the epipole. So why not take S to be E prime cross? Okay, we know that this is going to be a skew symmetric matrix. So good choice for S is taking this, and if you do that, then you get the camera pair P equal to I0 and P prime equal to this matrix. Okay, this is just we just substituted S in this formula. Okay, so this 9.14 is going to be we will refer to this later also. So whenever we say that given a fundamental matrix, you have a pair of camera matrices, we will usually be referring to this pair of camera matrices. Okay, so given F, you can always construct this pair, and this is the one that we will refer to. Although there is, of course, the entire family to look at. And finally, the most general solution, okay, so that family can be that family of matrices or family of pairs PH P prime H, okay, can be described here. Okay, so this formula here, so P is still I0, and this multiplication by lambda to E prime. Okay, so look, just look at the difference between this P prime and this P prime. Okay, so we are saying that applying all homographies to P prime, okay, will generate matrices of this form. Okay, so the only difference between this choice and the rest of the family is going to be a choice of a vector V and a choice of a scalar lambda here. Okay, all other P primes are going to look like this. Okay, so but anyway, 9.14 is what we will require most often. Okay, so although this is the general solution, right? So so this is how you can retrieve P and P prime, the camera pair, from a given fundamental matrix. Now we want to do the same when we are given the essential matrix. Okay, so to retrieve P and P prime from an essential matrix, since we have this nice factorization of E into a skew symmetric matrix times a rotation matrix, we are going to use that, and it turns out that that gives us very nice formula for P and P prime. So first, this is to be noticed that suppose the SVD of E is given by U times this diagonal. So we know that the SVD, the singular values are 2 equal and the third one is 0, right? So you can, when they are equal, you can always pull out the scalar, the requisite scalar, and make it in this form, right? So you can take the SVD of E to be of this form. Okay, then there are two possible factorizations of E as S times R. Okay, so those two possible factorizations are, well, S will always be of the form U, Z, U transpose. Okay, where Z is this matrix here, where Z is this 3 by 3 matrix. Okay, so S will be U, Z, U transpose, and R could be one of UW V transpose or UW transpose V transpose, where W is this 3 by 3 matrix here. Okay, so what this result is saying that any essential matrix can be factorized into S times R, a skew symmetric times a rotation matrix. Okay, in this way. Okay, so your skew symmetric matrix is just this, R can be one of these. Okay, so that gives a very strong handle on how E will look like, right? So once we have this, we can we get the following result, that given any essential matrix E, again written in this form, and if you fix the first camera matrix to be this canonical matrix, okay, then there are 4 possible choices for the second camera matrix. Okay, so this can, I'm not going to prove this, but this can be proven using these two. Okay, so there are 4 possible choices for the second camera matrix given here. Okay, so essentially this is saying that when you, if the essential matrix is given to you and you decide to have your reference camera being the canonical camera, then there are only 4 possible pairs. Okay, so this is unlike the more ambiguous family that you get from the fundamental matrix, right? So unless you either have to make this choice, okay, you either have to make this choice here, okay, or you have this entire family of matrices, correct? But in case of the essential matrix, there is no such thing. You have only 4 possible choices of the camera pairs. Okay, so the essential matrix definitely gives you a stronger or fewer choices to look at. Okay, so any questions so far? I mean, you might have questions that you might have to read up a bit and then ask me. But if there are any quick questions, we can deal with them now. So from all this, you simply need to understand that, okay, from the fundamental matrix and from the essential matrix, you can retrieve the camera matrices for the system up to a certain ambiguity. If you have essential matrix, okay, you are more or less good. Okay, but if you have the fundamental matrix, you have to work with this ambiguity. Okay, unless you are in a position where you can make a choice of the canonical camera as your reference camera. Okay, and then you can work like this. All right, so then moving ahead, now what we want to talk about is how to compute the fundamental matrix from point correspondences. So we have not yet talked about how to compute this. Okay, so theoretically we sort of know that we will or how this f is derived, correct? If you know the epipole and you know the calibrations of the 2 cameras, then we have a formula for f. Okay, but suppose we don't have the calibration, suppose we don't know anything and we just have the 2 views, which means we just have the 2 images. Okay, then from point correspondences can we compute f? So this is in spirit of the homography computation earlier. Okay, so using the direct linear transform. Okay, so in that spirit, can we also compute the fundamental matrix? So that is what we are talking about here. Okay, so given a pair of images, the fundamental matrix can be computed from a pair of from a set of matching points. Okay, so how to do that? You should recall that the fundamental matrix has 7 degrees of freedom. Okay, so this is something we discussed in the previous lecture, which means it requires at least 7 pairs of matching points. So if there are at least 7 pairs of matching points given to us, then theoretically it should be possible to derive this fundamental matrix, right? So we'll see how to do that. So we introduce some notation. So suppose we are looking at the pair of matching points x and x prime. Okay, I'm using this underline to differentiate it from the notation that I'm going to use in a moment. So for a pair of matching points x and x prime, let's write x as xy1. Okay, so this is remember this is these are image points. So these are on a plane or the projective plane P2, correct? So they will have projective coordinates xy1. Suppose x prime has projective coordinates x prime y prime 1. Okay, then x prime transpose fx will be just this multiplication. Okay, and this can be simplified. So if you just simplify this, okay, and write down terms with these coefficients. Okay, so f11 is going to appear with x prime x. Okay, f12 is going to appear with x prime y, and so on. Okay, so I've just written that equation here. Okay, so this matrix multiplication equal to 0, 0, 0. That will give us this equation. Okay. So now we can express this equation as this inner product. Okay. So what we can do is take the elements of f in a row major form, which means that you just write all rows one after the other and look at that column vector. So this is f, okay, and the coefficients I have written here. Okay, so this same equation is expressed as an inner product in this form. All right, now this is for one pair of correspondences x and x prime, correct? Now if you have more correspondences, if you have a set of n matching point pairs, okay, then for each matching point you will get such an equation. Then you stack them and get this kind of system. Okay, so you have this vector f here. Each time you will have a 1 by 9 row, and then you can stack whatever n correspondences you have, you stack them here. Those, so that you will get a n cross 9 matrix A here, multiplied by f should be 0. Okay, everything clear so far? So what we have here is a homogeneous, remember everything is in homogeneous coordinates. F was in homogeneous coordinates and these two. So what we have here is a homogeneous set of equations. Okay, and this, if you can find f will be determined up to a scalar. Okay, so now let's see what are the various possibilities for the rank of A. Okay, so what are the various possibilities? Of course, you can have rank of A equal to 1, 2, 3, 4. But will 1, 2, 3, 4, like things like that yield anything useful for us? If the rank of A is 1, is that going to help us? Hello? I wonder if the class is still here.
Yeah.
Yeah, so I'm asking if the rank of A is 1, is that going to help us?
So then the null space will be of dimension 8, right? We can't really say anything about f up to a scalar.
So what should be, what of the rank of A is 6? Okay, this is, I think, some 11th standard question now. What will happen if rank of A is 6? No, you don't know what will happen if rank of A is 6? What kind of system of equations will this be?
Like there are going to be infinite solutions for f in that. Actually,
Inconsistent set of equations.
Infinite.
Do you mean like degenerator?
So this will be an underdetermined system of equations, right? So that is going to be a useless situation for us. If the rank of A is 6, no good. How many minimum should you, what should be the minimum rank of A to make for this set of equations to make sense or to give us some sensible solution?
8, ma'am.
8, why do we need 8? What is the degree of, how many degrees of freedom does F have? Well, F has 7 degrees of freedom, right? So if you have 7, the rank of A being 7, okay, then you can uniquely determine this F. Correct? So we'll see later what we'll do if rank of A is 7. Okay, so then this F is easily determined. If rank of A is, so the rank of A must be greater than or equal to 7 for this system of equations to make sense. Okay, and then if rank of A is 8, well, then the null space of A is only one dimensional, and so F is clearly, I mean, you can take a vector in that null space and make that, and that will be your solution F. So if rank of A is 7, the null space is 2-dimensional, and you have some space for constructing F. If the rank of A is 8, the null space is 1-dimensional. Again, you have space for constructing F. If the rank of A is 9 or more, okay, then what you will have to do is use a least square solution. Okay, so that least square solution will proceed exactly like what we did in earlier when we were doing homography. Okay, you find a least square solution so you minimize norm AF subject to the constraint that norm F is 1. Correct. So the least square problem can be, we have seen that it can be simplified to this least square problem. And we have also seen what is the solution to this least square problem. It is the smallest right singular vector of A. Correct. So this we have already described before. So if the rank of A is 9, then the smallest right singular vector will give you your F. Okay, and this idea is what forms the crux of what we'll see later, the 8-point algorithm. Okay, so and the same thing can be done even when the rank of A is greater than 9. Okay, so strictly greater than 8 is what I should say. If the rank of A is strictly greater than 8, then this is how we can proceed. Okay, now even though you can just proceed this way, this is not suggested because this is not numerically stable. So what one has to usually do is normalization. Okay, so one will always carry out a normalized computation, which means you first normalize the data, carry out this computation, find the solution, and then denormalize. Okay, so this is also something we have seen before. So I have just copied this algorithm which says, so how to compute F from point correspondences. So this is the so-called 8-point algorithm. Okay, you're given greater than or equal to 8 image point correspondences. Okay, then you first carry out data normalization. Okay, so this I have described earlier. You transform the image coordinates, okay, where according to, so if you remember, we had this picture earlier. So you have xi, you transform this to txi, okay, and then you have xi prime, you transform this to T prime xi prime. Okay, so this is your new xi hat, and this is your new xi prime hat. Okay, so you make this transformation. Then after this transformation, you compute the map using these transformed pairs. Okay, so how is that computation done? That is this solution that I described just now. Okay, so this linear solution, which is the smallest singular vector corresponding to or for the matrix A hat. Okay, see, A hat is composed from these matches, not the original A. Okay, so we do want to solve this one A, but now see, this was for the original points. You have to compute A hat for the normalized points and solve with respect to that A hat. Okay, so once we solve A hat, then there is something else. This step I'm not going to talk about much. Okay, this is going to make sure that determinant F, we know that F is a singular matrix, right? We have seen this earlier, that the fundamental matrix is singular, it is rank 2. Okay, to make sure that you do have a singular matrix, this is constraint enforcement. You replace F hat by F hat prime such that this determinant is 0. Okay, in case you end up with a matrix whose determinant is non-zero. Okay, so you do make sure that you have a rank deficient matrix F. Okay, so this constraint enforcement step is also carried out. Okay, after this, and then denormalization, which means you have found a solution for these pairs, and now you apply the inverses of these and denormalize to find a solution for the original pairs. So this is the 8-point algorithm for computing the fundamental matrix from image pairs. Okay, and in most situations, this algorithm is quite successful. Okay, however, if you look at the text, then there are many so normalizing and using the 8-point algorithm is something that is done very commonly. Okay, but another very common thing for numerical reasons as well as for accuracy reasons, and that is the maximum likelihood estimation method. Okay, where what one does is one tries to minimize the reprojection error. Okay, so reprojection error in any situation means that you have some pair of, or you have some data, you have computed some map, you apply that map, okay, and see what is the calculated result, and then you see what is the expected result. The difference between the calculated and expected result is called the reprojection error. Okay, in general, this is definition. So minimizing that reprojection error is a sort of general strategy using maximum likelihood estimation, which is used even in calculation of homography, in the calculation of camera matrix, as well as in the computation of fundamental matrix. Okay, so these two things, either you use this normalized 8-point algorithm or the MLE, which hinges on minimizing the reprojection error. Okay, so one of these things are used for computation. Just like the reprojection error, one can also use MLE with something called a Sampson error. Okay, so I'm just throwing these words because you might see these when you are using some packages or some functions from OpenCV. Okay, so just like reprojection, there is another called Sampson error, which is also very commonly used in these kind of computations. Okay, so that I'm not going to talk about at all. Okay, so I'm just going to talk about this normalized DLT sort of algorithms. And if you want to look at the other family of algorithms, then I would suggest you do it on your own, or we might have to spend some time in a tutorial or something for that. Okay, all right, so now that we have seen at least one method, yeah, so there are, here I'm talking in a bit more detail about a rank K equal to 7. So in this case, the dimension of the null space is going to be 2, and suppose you have two generators, F1 and F2 for that null space. Okay, then you can look at the space. So the space of solutions will be of this form here. Okay, for if the small f1 and small f2 are those length 9 vectors, right? So those correspond to some matrices. Let me call them F1 and F2. Okay. And the only constraint that has to be satisfied by the solution is that the determinant of this must be 0. The determinant of the solution that you get. Okay. So this linear combination alpha F1 plus 1 minus alpha F2, this linear combination should have determinant 0. Okay. So if we put this constraint, then this turns out to be a cubic polynomial in alpha. If it has complex roots, they are ignored, and real roots could be either 1 or 3 in number. Okay, so depending on 1 or 3, you will get 1 or 3 solutions to this system of equations in the case rank of A is 7. Okay, so if there are 1 real root, then you have only 1 solution for this. If there are 3 real roots, you will get 3 possible solutions for F. So that is what happens if the rank of A is exactly 7. Okay, and the other cases we covered. Okay. All right, any questions here? Either in the algorithm or in general computation of F? Okay, so if you have no questions, let me move on to the last part, which is reconstruction. Okay, so this I'm going to leave a lot of gaps here. We will just look at the outline of this because there are a lot of details to be filled in here, and that's not possible in 1 or 2 lectures. So what I would rather prefer to do is give you an outline of the whole process. Okay, and then when we have done some segmentation and we want to do some later algorithms, like algorithms which are meant for such reconstructions, okay, then we will come back to this. So this is sort of the naive idea for reconstruction from 2 views, which is you compute. So from 2 views, we have seen how to compute the fundamental matrix. So you compute that fundamental matrix from point correspondences. Then once you have F, you can compute the camera matrices P and P prime. That also we saw that we can retrieve P and P prime from F. So you do that step. And now once you have P and P prime, okay, then you remember your camera geometry. The situation is that you have, see, you want to reconstruct this point X in space, which projected onto your point X and X prime in the 2 views. Correct? So you want to get this back. Now what you have constructed is P and P prime. You know P and P prime, you know X and X prime. Then the idea is simply you back project these 2 rays. Okay, you back project X, you back project X prime. Okay, these 2 rays should intersect. Correct? They are going to be, these are all going to be coplanar, and we are doing projective geometry. So if you have any 2 lines on a plane, they will intersect. That intersection point is your space point X. Okay. So using this back projection, you can reconstruct this point X. So the only information that we require for doing this entire process is a set of point correspondences. Right? You have to be given a set of point correspondences, and this idea you can, if it gets executed properly, you will be able to compute the space point for a given set of point correspondences. Okay, so is this idea clear? This idea is called triangulation. Okay, so this idea for step 3, that you back project the rays and find their point of intersection. This idea is called as triangulation. Okay, but yeah, so one before I go ahead, the only points in 3 space that cannot be found by this idea are points on the baseline. And you remember what the baseline is? So in this configuration again, so we have these, sorry. So we have the point, the line joining the 2 camera centers. right? So let me just draw it this way, C prime, and here you have C. Okay, so this line that joins the two camera centers, that's the baseline. So now you can, the baseline intersects the two images in the two epipoles, if you remember. Okay, now you can imagine that since all points on that line just lie on that line, right? They are only collinear. You don't have any other information about them. So there is, you cannot recover them from this back projection idea. Okay, so those are the only points that cannot be found in this way. So this is just something that you have to keep in mind. Okay, now there are this sort of naive idea. This is naive for two reasons. Okay, it has two main problems. One, there are inherent ambiguities in this. Okay, so yeah, I'll talk a little bit about this now. Okay, and this, the second one, the failure of back propagated rays to actually intersect. So theoretically, yes, they are coplanar, and they should intersect, and you should be able to find this point. But in practice, what happens is that, see, for first of all, you're doing this all with these given point correspondences. Okay, so if there is any error in measurement here, okay, then that will lead to this back projected rays not intersecting. Okay, so they will be skew and they will not intersect. That, so any error in measurement here will first of all give rise to that. The other thing is that these are all numerical computations. Okay, so this is all being done in floating point arithmetic. So that is another reason why you will most likely have rays that will not intersect. Okay, so the failure of back propagated rays to intersect comes because of these practical considerations of from measurement errors and numerical rounding of errors. Okay, so both kind of errors cannot be ignored in real life situations. So this kind of idea, even though it seems easy and idealistic, it doesn't work because of these reasons. Okay, so the second reason is quite easy to imagine. Okay, the first one, what are the inherent ambiguities? Okay, so if you want, so now just think that you have two images of a certain object or of a certain place. Okay, and you want to reconstruct the 3D. So first thing, is that without having any knowledge of the scene's placement in the 3D world, okay, there are some things that you will never be able to tell. For example, if you have two views of a certain room, you will never be able to tell what is the latitude and longitude of that spot. Right? If you have no other information and just two views of a room, this information is never possible. You cannot find latitude and longitude or the absolute position, absolute orientation, whether that room is facing north, south, east, west, whichever. Okay, these kind of things you will never be able to give without having some extra information about the scene. Okay, so that is an inherent problem which you cannot solve without external information. Okay, just from these two views of an object. Okay, so that is one thing. So what we mean, how to express this mathematically, we express this by saying that the scene can be determined at best up to a Euclidean transformation. Okay, Euclidean transformation of the world frame. What is Euclidean transformation of the world frame? Which means some rotation or translation. Okay, so you can determine the orientation and position of an object up to Euclidean transformation. Is this clear? The mathematical statement clear, and why it is that way? Yeah, so that's the first thing to note. Without external knowledge, you can determine only up to Euclidean transformation. Then the other thing to keep in mind is you also can determine only up to a similarity transformation, which means you cannot tell from two views of an image what is the scale of the image. Okay, so you always have to use some kind of external information For example, if you know it is the image of a room, okay, then you have some pre-knowledge that maybe, or we know usually the distance between, for a general room, the distance between the floor and the height could be up to 3 meters or something like that. Okay, so this is some information that we have as a preconceived notion, or some information that is provided to us. But otherwise, if just two views are given to us, that the image could be from a toy, so it could be the actual distance between the floor and the height, between the floor and the roof could be like 5 centimeter because it's from a toy, or it could be 5 feet because it's a small room, or it could be 5 meters because it's a large room. Just from two views of that object, you cannot determine exactly what the height is. Okay, so this we can express by saying that the knowledge from the image, the knowledge of the scene that we can determine from the image, is only up to a similarity transformation. Okay, so not just up to a Euclidean transformation, but up to a similarity transformation. We cannot even determine the scale. Okay, so everything is up to scale. And going ahead of that, it is even more ambiguous in the sense that the reconstruction, if the cameras are uncalibrated, okay, so these things, even with a calibrated camera, you can determine up to scale. Okay, but if your cameras are uncalibrated, which means you know nothing about the positioning of the cameras with respect to the world coordinate frame, and you also don't know the intrinsic parameters, then in fact the construction that we do is only up to a projective ambiguity, which means that the actual scene will be a projective transformation of what you will determine. Okay, or vice versa, what you will determine will be true only up to a projective transformation, which means it could be a distortion of the actual scene. Okay, a projective distortion of the actual scene. Okay, so these are ambiguities that you cannot get rid of with this kind of construction. If you do triangulation, okay, this kind of construction, you cannot determine the actual scene up to projective, or you cannot clear these projective ambiguities. Okay, so are there any like, are you able to imagine these situations? Are you have doubts about this? We have time, so we can up 5-10 minutes, so we can have a discussion if you have questions about this. Is it clear to you why there is an ambiguity? The actual scene might be something, and but from the images you can only determine up to, you cannot determine scale, that is quite obvious, but you can also determine what is before, what is after. Okay, that is an example of projective ambiguity. Okay, those you saw those images earlier, right? What was it called? In the first homework you had some what is it called?
Monastery images.
Hmm?
Those 3 images in which we have to make a colored images for monastery.
No, not monastery. The last one, the last exercise in the homework month, which was, so you see something, but it is actually something else. Yeah?
Illusions.
Illusions. Yeah, sorry, that's the word. Illusions I was looking for. So you have these visual illusions that come into play. Okay, and that's because you can determine only up to projective ambiguity. Okay, so something might be actually far, but it might appear to be close. That's an example of projective ambiguity. Okay, so there are these projective ambiguities also which cannot be resolved with two views. Okay, you require more than two views, or you require some more sophisticated ways of reconstruction to get rid of these ambiguities. Okay, so triangulation, although it looks like a very simple idea, it doesn't work for these reasons. Okay. Whatever I said about these inherent ambiguities, that is being able to determine up to Euclidean or up to Euclidean transformation or up to similarity transformation or up to projective transformation, all this can be made mathematically precise. Okay, so this is the content of chapter 10 in this book. Okay, so this is chapter 10 of this book. Okay, where the authors talk about the inherent ambiguities and what are the various things that can be done to get over these. Okay, and about the failure of backpropagated rays to intersect. Okay, and so coming up with different algorithms to take care of the fact that, you know, these rays may simply not intersect because of measurement errors. Then what do? Then you have to come up with a different way of computing the structure. So this is the content of chapter 12. Okay. So modulo all this, okay, if one still wants to work with the triangulation idea, in certain situations, it is still possible to work with this, but not in the naive manner. You know, there are some extra steps that need to be taken. Okay, so if one still wants to make the triangulation idea work, it can work with some extra steps. So I will just go through this algorithm quickly, okay, because I haven't talked about the details of all this, right? So given two uncalibrated images means you have the images, you have the camera matrices, but you do not have the calibration of those camera matrices. You want to compute a metric reconstruction. What do we mean by a metric reconstruction? This means that you should be able to measure from these two images, you should have enough information to measure the actual distance between those world points. Okay, so you want to have a reconstruction which is metrically correct. So you want to compute a metric reconstruction of the cameras and scene structure. That is a reconstruction which is within a similarity transformation of the two cameras and scene structure. Okay, so there is no projective transformation. It should be within a similarity transformation. Okay, so if you are given one piece of additional information, that is, if you are told what is the scale of the scene, from that you should be able to tell all the other metric properties of the scene. Okay, so the first step is the same. Okay, you compute the fundamental matrix, you retrieve the camera matrices, and you do triangulation. You do the naive triangulation for each set of point correspondences. You try to compute these points xi. Okay, but now the thing to do is to refine these points xi's, okay, step by step. So first you rectify the projective reconstruction. So which means you try to get rid of the projective ambiguity. This can be done in two ways. There is a direct method. Okay, so I'm not going through the details. And there is a stratified method which consists of two steps. Okay, so in this way, one can get rid of the projective ambiguity. Okay, and then you are left with similarity. Okay, so you will get a reconstruction which is good up to a similarity transformation. Okay, and that is called a metric reconstruction. Okay, so yeah, if anyone or if the class in general is interested in going through the details of this reconstruction, we can again come back to this. Okay, but for now I will stop with this. Okay, and although we haven't done enough justice to the idea of reconstruction, a lot of computer vision is about reconstruction. Okay, so we will do some image processing and then try to come back to this topic. Are there any questions at this point? Okay, so if there are no questions, I will stop recording. Oops. Sorry. How do I stop recording? Yeah, stop. Okay, so If there are no questions, I can end the meeting. All right, I'll see you on Tuesday. Please do look at the practice questions that I will post in the on Moodle. Okay, and let me know how you are doing with it, so that if a tutorial is required, then I can try to set it up sometime early in the week. Okay, not on the evening before your quiz. Okay.